So after you have gone through and answered all these questions, you should have noticed that when you were to draw your segment bisector, you should have had this at a right angle, right? And you also should have noticed that all your points on that line were the same measure from your point to A and to B. So let's see if I can draw this real quick. Okay, so if I were to draw this, let's say I was using a straight edge like you should have. Okay, and here's my right angle. If I were to pick 3 points, 1, 2, 3, the distance from your first point to A and to B, oh wow, these should have been the same exact length, okay? We're going to talk about that a little bit. So, a segment bisector is something that you talked about in, I believe, Chapter 1. A segment bisector is something that intersects a segment at its midpoint, okay? So here, this segment bisector, our midpoint is P. So a segment bisector intersects at a midpoint, but a perpendicular bisector intersects at the midpoint as well, but when it intersects, it's a 90-degree angle because this line right here, CP, is perpendicular to AB. So CP is a perpendicular bisector to AB. Now, just like you did in your picture, when you draw or when you measure the distance from this point C, which is on the perpendicular bisector, to point A and to point B, they should be equidistant, which means that the point is the same exact distance from each figure. So here our figure is C. Okay? Equidistant also means that points on the perpendicular bisector of that segment are equidistant from the segment's endpoints. Okay? So this is exactly what this picture is representing. So in your textbook, this is also in your packet, we have Theorem 5.2, the perpendicular bisector theorem. This theorem says that in a plane, if a point is on the perpendicular bisector of a segment, okay, so this point C is on this perpendicular bisector, then it is equidistant from the endpoints of that segment. So here our perpendicular bisector is CP, and it bisects AB, so therefore CA and CB must be equidistant. They have the same length. So in this example down here, BD is a perpendicular bisector of AC. Find AD. Okay, we got to find the length of this side. Okay, again, sides do not have degree, they have units of measure, of length. Okay, so if BD is a perpendicular bisector, okay, then we know that these two sides are equidistant, right? Should be the same, DC should be the same as DA. So therefore, we can set them equal to each other by this perpendicular bisector theorem above. When I do that, I get 5x equals 3x plus 14. Okay, so all this is a mini theorem. All I did was I substituted my values in and I solved for x. Okay, but you're not done. X equals 7. You are asked to find the length of AD. So you need to take x equals 7 and plug it in into 5x. And you should get the length of AD equals 35. Now pause the video and do this exercise. It's very similar to the one you did before. Okay, so when you measured the distance from point A, from this point to point A and to point B, you should have found that they have the same measure as well. So this point is equidistant from A and B. So what did you think? What do you think that means? This point is not particularly on my perpendicular bisector, but yet it has the same properties, right? So let's look at that. This leads us into our next theorem, which is the converse. Okay, so the converse is just you're switching the hypothesis and the conclusion from our first theorem, Theorem 5.2. So in a plane, if a point is equidistant from the endpoints of a segment, okay, so here this point, just like you did in your own picture, is equidistant from these two endpoints, then it is on the perpendicular bisector of that segment. So what that means is this point, okay, if we were to extend this line CP, this line would cut right through that point. So therefore this point right here, D, would lie on this perpendicular bisector. Okay, so it's just the converse. The perpendicular bisector theorem said if this point is on our perpendicular bisector, then these lines are equidistant. Now we're saying if this on this point, okay, our lines are equidistant, then this point must lie on that perpendicular bisector. Okay, so it's just switching the hypothesis and the conclusion. So if DA is equal to DB, then D lies on the perpendicular bisector of AB. Okay? Let's look at an example. So in the diagram, X or WX is a perpendicular bisector of YZ. Okay? Now we have to look at what segment lengths in a diagram are equal. So we know that YV and ZV are equal, right? I mean, it tells us that. So we know 1. So we know that YV is equal to VZ. Okay? What about, okay, now let's look at some of our other sides or our lines in this picture. What do we know about, do we know anything about WY or WZ? Is there any way that we could prove that these two lines are equidistant or that they're congruent? Well, there is, because if this line WX is a perpendicular bisector to YZ, then we know by our theorem 5.2, the perpendicular bisector theorem, that these two lines have to be equidistant. Okay, this point lies on that perpendicular bisector. Therefore, the length of this line and the length of this line must be the same. So by theorem 5.2, we know that YW is equal to ZW. Okay? We also know that XY and XZ are congruent. If this is a perpendicular segment bisector, or even just a segment bisector, to bisect something means to cut it in half. So if this line is being bisected, this point X is our midpoint. Therefore, these two lines have to be congruent. So YX is equal to XZ. Okay? Now let's look at our point V. It's asking us, is V on WX? Alright, well, if we know that this line, YV, is the same as this line, ZV, then this point V must be on this perpendicular bisector. This is the converse that we just looked at, okay? If this point to the two endpoints of this segment are equidistant, right, which they are, they're both 25 in length, then if this segment, this perpendicular bisector were to be extended, it would go right through that point V. So this is yes, okay, by our converse theorem 5.3. All right, let's look at this example here. In the diagram, JK, okay, is a perpendicular bisector. So JK is a perpendicular bisector of NL. What segment lengths are equal? Okay, well, this is just like what we talked about before. If this is a perpendicular bisector, then these points, these lines are equidistant, so we know that these sides are equal. If this is a perpendicular bisector, this JK then cuts NL in half at this midpoint J, so we know that these segments are equal. And we also can say that segment MN is equal to segment ML because it tells us that they're the same measure. Okay, they're both 8 units long. Okay? Also, let's talk about 3 here. Okay, we know that M is on JK because this is, again, the converse theorem 5.3. At this point, if we extend these lines to our endpoints of this segment, and they are equidistant, so they are the same measure, then this point M must lie on our perpendicular bisector. So if I were to extend this perpendicular bisector JK to go through M would fall on that perpendicular bisector by our converse. Okay, so again, it's just switching our hypothesis and our conclusion. So here, we're saying that K is on our, we're told it's on our perpendicular bisector, right? If it's on our perpendicular bisector, then these lines are the same, they're congruent, they're equal, okay? The opposite says if our lines are equal, then our point is on our perpendicular bisector, okay? So let's go back to 2. How do we find NK? Well, we know that NK is equal to KL. NK equals 6x minus 5. KL equals 4x plus 1. So we're just going to set them equal. We know they're equal. And solve for x. So subtract 4 from both sides. Or 4x from both sides. And then I'm going to add 6 to both sides. Then I'm going to add 5 to both sides and get 2x equals 6. Divide by 2 and you get x equals 3. Okay, well, we found what x is, but it's asking us to find what nk is. So we have to go ahead and take x and plug it back in for nk. So nk equals 6x minus 5. So that's going to equal 6 times 3 minus 5. Okay, and that's going to give us that nk equals 13. If it would write, that would be great. Okay. Now you're going to go ahead and you're going to go to your next problem, and you're going to go ahead and try to do this without your notes. I want you guys to go and fill in the definition of a perpendicular bisector. Okay, we're going to talk about this point of concurrency later on today, and then go ahead and fill in what the perpendicular bisector theorem is and the converse of the perpendicular bisector theorem.